So in this video, we're going to go over how to test for even symmetry. Before we test for even symmetry, we probably should get an idea for what even symmetry is. And all even symmetry means is bilateral. It's a type of bilateral symmetry. So we're looking for symmetry with respect to a line that we can establish on the object. So for example, with the ladybug here, if you draw a line down that crack between its wings, you'll notice that the one side, the right side in this case, is a perfect reflection of the left-hand side in that line. So this ladybug has bilateral or even symmetry. This butterfly has bilateral or even symmetry. This starfish has bilateral or even symmetry. It's a reflection of itself in a line that I can establish. This bridge also has even or bilateral symmetry. The right-hand side appears to be a reflection of the left-hand side in this vertical axis that I've established. When we're working with functions, we are after having symmetry with respect to a specific line, and in this case the line is the y-axis. So if we have a function that is a reflection of itself in the y-axis, then we're going to say that that function has even symmetry. So this is a type of bilateral symmetry. So this picture here is a picture of a function x to the fourth minus 4x squared that clearly exhibits symmetry with respect to the y-axis. So it has even symmetry. We can see that it has even symmetry. And the key that we want to notice is that if we take any value for x, so here x is 2.2, and we look at the opposite of x, so the opposite of 2.2 is negative 2.2, we see that the outputs have to be the same. What's driving this is that because it's a reflection of itself in the y-axis, the distance between this point in the y-axis, that 2.2 units, when you reflect this point over the y-axis, the reflected point is going to be 2.2 units also, but because it's to the left of the y-axis, it is a negative 2.2. So when you walk through this graph, you input negative 2 or 2, the output is 0. If you input negative 1 or positive 1, the output is negative 3. And so up here, this definition generalizes this idea by saying, hey, notice that if the function has even symmetry, or if it's an even function, when you plug in the opposite of x, you get the same output as when you plug in x. And that's what this picture right here is showing us. You plug in x or the opposite of x, the outputs are the same. And remember that the function notation f of x represents an output and the x is the input variable. So what we want to be able to do is test for even symmetry without having to look at the graph of the function. So if I take the same function that I had on the previous slide, but I don't show you the picture of it, and I just say use the definition of an even function or even symmetry, use the definition to verify that the function is even, what we want to do is show that f of the opposite of x equals f of x. So to do this, you start with taking the left-hand side of the relationship that you see here, and you just write it down. You say, hey, f of the opposite of x. Well, what does that equal? Well, we know that when we have something going into the input position with function notation, that it just means to go to the function itself and replace every occurrence of x with whatever is inside of the parentheses. So in this case, every occurrence of x, so we have x to the fourth minus 4x squared, every occurrence of x has to be replaced with the opposite of x. And then what we want to recognize is that the opposite of x is really just negative 1 times x. So the opposite of x is really just negative 1 times x. And exponents can be moved in over a multiplication symbol, so we know that this right here is really negative 1 to the 4th power times x to the 4th power minus 4 times, this is really negative 1 being squared times x being squared. And we want to recognize is that negative 1 to the 4th power is just negative 1 times itself 4 times, and every pair of negative 1s that we get in a product is going to give us a positive 1. Every pair gives us a positive 1. So negative 1 to the 4th power is just positive 1. So negative 1 to the 4th power is just 1 times x to the 4th minus, and negative 1 squared would be the same deal. If you take negative 1 and you square it, you're just multiplying negative 1 times itself, which is going to give you a positive 1. So this is really just 4 times positive 1 times x squared, which simplifies to x to the 4th minus 4 times 1 is 4x squared. And then you look at the result, you'll see that it's what f of x is. X to the 4th minus 4x squared, which I have right here, is just f of x. And then from that I can draw a conclusion. I can say because f of the opposite of x simplifies to f of x is even. It's an even function. We don't want to have to expand negative 1 every time like this. So what we really want to recognize is that anytime we raise a negation to an even power, if this power is even, then we're going to get an even number of pairs of negative 1s, and every pair of negative 1s is going to give us a positive 1. So the result of raising a negation to an even power is always going to be that you get a positive 1 out of it. And usually you would skip these steps and just go straight to the result. So we'll do one more example. So we're going to use the definition of an even function to show that x to the 20th minus 4 times the absolute value of x is an even function. So again, the definition of an even function says if the function's even, when you plug in the opposite of x into f, it needs to simplify to f of x. So you start with the left-hand side of this relationship. You say, hey, I'm going to plug in the opposite of x, and I want to see if when I do that it simplifies to f of x. So we go in, and everywhere we see an x, we have x to the 20th minus 4 times the absolute value of x. Everywhere we see an x, we replace it with the opposite of x. And then we simplify. So by the conversation that we had on the previous slide, we recognize this exponent is even. So the opposite of x to the 20th power is just going to be x to the 20th power, because negative 1 to the 20th power is going to be positive 1. And over here, we want to recognize that when we're working with the absolute value of the opposite of x, this is really just negative 1 times x. And absolute values, the absolute value of a product can be broken into the absolute value the product of the absolute values, sorry. Didn't write that very well. See if I can write this a little bit better. The product, the absolute value of a product can be rewritten as the product of the absolute values, and the absolute value of negative 1 is just positive 1. So the absolute value of negative 1 simplifies to positive 1, and that's times the absolute value of x. And we take this one more step. We get 4 times 1 times the absolute value of x after we've simplified everything. And when we get to this step where we've simplified the negation as much as we can, we want to look back up here and see if we have exactly what we have here. And if we do, then we know that this statement here is the same statement as f of x. So if I bring this down, I'm really noticing that I'm saying f of the opposite of x simplifies to f of x. So f of x is even because f of the opposite of x equals f of x.